We make phone calls every single day, and we just kind of expect them to work, right? But have you ever stopped to think about what it really takes to keep just one single critical call connected while it's moving through a chaotic, bustling city? Well, today we're going to find out.
See, behind that simple act of just talking on your phone, there is this hidden world of engineering. It's an unbelievably powerful and intelligent system, working silently in the background, managing every single connection. And today, we're going to follow one incredibly urgent call to understand exactly how this invisible network pulls it all off.
And this is our call. Meet Ananya. She's racing to the hospital, and this connection to her brother, Rahul, is absolutely everything right now. The instruction is so simple, but the engineering challenge is immense. Don't cut the call. For the network, this is now its one and only job.
Okay, so how does a call like this even begin? Well, first, Anyanya's phone, that's the mobile station, sends a signal out to the nearest cell tower, which we call a base station. From there, that signal gets routed through the Mobile Switching Center, or MSC. You can think of the MSC as the central brain of the whole operation, connecting her call all the way to Rahul's phone.
Now you might be wondering, a city has millions of people, but there's no way there are millions of phone channels, right? So how does that work? The whole system is built on a clever principle called trunking. It's basically a smart bet, a statistical certainty really, that not everyone is going to try and make a call at the exact same time. This lets a huge number of people share a much smaller pool of channels. It's all about efficiency. But what happens during rush hour, or after a big concert, when everyone is trying to call at once? Well, networks are designed for what's called a grade of service, which is the chance your call might get blocked. They aim for this to be super low, like 2%, but super low isn't zero. If that network gets overloaded, a call can get blocked, or even worse, the quality of a call that's already connected can start to tank. And, yep, that's exactly what's starting to happen to Ananya's call. The connection is getting choppy, Rahul's voice is cracking up. Now this isn't just some random static, this is the first sign of a classic cellular headache known as the near-far problem.
So here's the deal. Imagine you're trying to hear your friend whispering to you from across a really loud room, but someone else is standing right next to you, shouting in your ear. That's pretty much what's happening to Rahul's phone. A really strong signal from another nearby phone is literally drowning out the weaker, desired signal coming from the cell tower.
So how does the network fix this? This is where it gets really smart. The solution is called power control. The base station basically acts like a traffic cop. It detects that shouting phone and sends it a command saying, "Hey, you're being way too loud. You need to reduce your power." Just like that, the channel clears up and Rahul's signal can be heard again. Brilliant.
But this problem can happen the other way around, too, this time at the base station itself. Imagine a user standing right next to the cell tower, blasting it with a super strong signal. That powerful signal can make it incredibly difficult for the tower to hear the faint, quiet signal from someone else who's much, much farther away.
The fix for this is even more dynamic. It's called closed-loop power control. This means the system is in constant conversation with every single phone it's connected to. It's telling the close-by phones to quiet down and the far-away phones to speak up, all in real time. The goal is to make sure every signal arrives at the tower with about the same volume. It is a constant, delicate balancing act.
So a question you might have is, why not just have everyone crank up their power to the max? Well, that would be a huge mistake. See, to be efficient, cellular networks reuse the same frequencies in different geographical cells. If you boost the power in one cell, you're not just boosting your signal, you're also blasting interference into neighboring cells that are trying to use those same frequencies. The key thing to remember is that it's all about the ratio of signal to interference, not just raw power.
Okay, back to Ananya. She's driving, moving fast through the city. That power control system helped, but now as she travels from one neighborhood to another, the call is at its absolute most vulnerable point. The connection is fading again, and this time it feels like it's about to drop for good.
We've arrived at the make or break moment for any call on the move, the handoff. Think of it like a relay race. As Ananya's car leaves the coverage area of one cell tower, the call has to be passed like a baton to the next tower. And if that baton gets dropped, even for a split second, the call is lost, forever.
Now, the system totally understands this. It operates on a really important core principle. Dropping a call that's already in progress is a way, way worse failure than just blocking a new call from starting. So the network gives Ananya's critical active call priority over anyone else in that new area who might just be trying to dial out.
And how does it give her that priority? Well, the new cell tower she's driving towards has something called guard channels. These are amazing. They're like a reserved VIP lane on the highway. They're held open exclusively for incoming calls like Ananya's that are being handed off. Her call just slips right into this reserved channel, and just like that, the connection is saved.
And there are basically two ways of doing this handoff. The older way is a hard handoff, which is break before make. Your phone literally disconnects from the old tower for a split second before it connects to the new one. But most modern systems use a much smoother soft handoff, which is make before break. Here, your phone actually connects to the new tower while it's still connected to the old one, ensuring a much more seamless and reliable transition.
So the call is stable again, for now. But Ananya is getting close to the hospital, which is a really high-density area. I mean, think of all the people, patients, and doctors on their phones. The network anticipates this surge in traffic and knows it needs to increase its capacity right now. And it has 3 key techniques in its playbook to do just that.
First up, sectoring. Instead of one big antenna trying to cover 360 degrees, the cell tower divides its coverage area into sectors, kind of like slices of a pizza. Say 320-degree slices. Each slice can then reuse frequencies, which cuts down on interference and basically triples the cell's capacity without having to build a single new tower. Pretty clever, huh?
Second is the zone concept. This one is perfect for a big area like the hospital campus. You have one main base station that controls a bunch of smaller transmitters scattered around. As someone walks from one zone to another, the system just switches which little transmitter they're using. It's much simpler and way faster than doing a full-blown, resource-heavy handoff between 2 major towers.
And the third most powerful method in the arsenal is cell splitting. When a cell just gets too crowded, you literally split it into a bunch of smaller microcells. Each new tiny cell gets its own base station and its own set of channels. Now, if you cut the radius of a cell in half, you can massively increase the number of channels available per square kilometer. But, and this is a big but, you also have to seriously reduce the transmit power to keep these new tiny cells from interfering with each other.
Of course, this creates a whole new problem. What about Anya flying by in her car? If her phone tried to connect to every single one of these tiny microcells, she'd be doing handoffs every few seconds. So the network is smart about this. It uses a large umbrella cell that covers all of the smaller cells. Fast-moving cars like Anya's are assigned to the big umbrella, while slower-moving pedestrians connect to the little microcells underneath. But even with all this cleverness, you can still run into issues. There's a problem called cell dragging. This is when a phone gets, well, a little clingy. It stubbornly holds onto a signal from a tower it's already passed, even when it's deep inside a new cell's territory. To stop this from happening, the network doesn't just look at signal strength, it's also constantly checking the signal quality before it decides to make a handoff. Ananya is almost at the hospital. She's crossed the entire city, and now her call faces its final and biggest hurdle, an inter-system handoff. She has traveled so far that she's moving from the territory of one mobile switching center, one network brain, to a completely different one. This isn't just a handoff between towers anymore, this is a handoff between 2 massive independent systems. It requires perfect system-level coordination to keep this one call alive.
And it works. The call survives. That single connection was guided through intelligent power controls, it dodged waves of digital interference, it was given VIP priority through every single handoff, and it seamlessly navigated a complex, constantly shifting web of cells, both big and small. It's really the ultimate proof that this incredible, invisible system isn't just about technology and signals. It's about a promise to maintain our most vital connections, especially at those moments when one single call means absolutely everything.